All right. Sorry, I'm trying to get my camera better focus. All right, so you guys ask all the time, when am I ever going to use this in the real life? Well, this is it. So section 6.7 is all about applications. So there's nothing new in this unit. It's just going to be applying all of the different rules that we've learned to real world problems. Okay, so I'm going to work these, and then there's an unlimited amount of different types of problems that you could get with these. So you're going to have to critically think to solve these. All right, so this says Elvis is flying a kite. His hand is 3.5 feet above the ground. And he's holding the end of a 200-foot kite string. So here's the kite, here's the string, here's Elvis, and we know that his hand, so this distance right here, it's not on your diagram, is 3.5 feet. And the kite string is 200 feet. That little apostrophe-looking symbol is feet. And he holds this at an angle of 53 degrees with the horizontal. So here's the horizontal. So this is going to be my angle. And we actually call this an angle of elevation. E-L-E-V-A-T, elevation. Now, if you think about that, elevation means go up, right? So here's an angle and the angle's going up. And you're like, well, hold on a minute, because I know that when I draw angles, I draw them this way. But if you're looking at this from a straight line, okay, so here's my horizontal, the angle that we're going to make is going to go up. So think of this. It's elevation when Elvis has to look up. So angle of elevation, think about this like looking up. Okay, so how high is the kite off the ground? Well, here's what we know. We've got our hypotenuse right here. So here's a right angle that we have. We've got our hypotenuse right here. What I want is this distance. I want my y. So what I know is that my sine value, so sine of 53, is going to be y over my hypotenuse h, or if you're still using radius of r, that's fine too. So I know this value right here is going to be 200. So to solve this, I move my 200 over, and I have 200 sine 53 equals y. Now, this is in degrees, so we have to make sure that our calculators are still in degrees. So go into mode, and then go down here and make sure it says degree and not radian. Okay, super important. So now when I plug this in, I'm just going to say, 200 times sine of 53. Okay, now technically I don't even have to close my parentheses on that. I would if I did sine 53 times 200. Now I'll show you what that looks like. So what I get here is y equals 159.7. I'm just going to round to the 10th place. So look what happens if I put it in the other way. Sine 53 times 200. Now, I did not close my parentheses. Okay, so when I put this in, look at this value. That's like nowhere near what this height would be. But if I do sine 53 and I close my parentheses times 200, I go back here and get 159. So what I tend to always do, if I know I'm going to multiply by a sine function, I just put my number up front in case I forget to close my parentheses. I know that it's going to be okay. All right. Now, we can't forget that we've got this distance right here of 3.5. So I'm going to add 3.5, and that's this distance from the ground to this horizontal. So if I have 159.7 plus 3.5, then the total height here, how high is the kite off the ground? 163.2 feet. Real world problem, we've got to have a unit on it. Okay? All right, let's look at this next one. Oh, here we go, angle of elevation. So we know right now, angle of elevation tells us that we're going to look up. And so, sorry, I was getting my highlighter here. So angle of elevation. We're going to look up. So it says a steel cable zip line is being constructed for a reality TV show. The high end of the zip line is attached to the top of a 50-foot pole. So here's the pole. Okay. Here's the top of the zip line right up here. While the lower end is anchored at the ground to a stake 50 feet from the base. So here's the stake. Here's the base of my pole. So here's the pole. Here's the base. Okay. Find the angle of elevation of the zip line. So if I want the angle of elevation, and remember what we said is angle of elevation means we're going to look up, that is going to be this angle. So when we're worried about which angle is it going to be this one or this one? Remember, we're looking up. So since we're looking up, this is my angle of elevation. Okay, so find the angle. Well, what I know here is I have opposite over adjacent. So I have y over x, and I know that that's tangent. So tangent is going to be y over x. In this case, it's 50 over 50. So what we know is that we have tan of some angle is going to equal 1. And hopefully you don't even need to think about what this looks like, but with tan of this, it's going to be 45 degrees. And I know this because this is a 1 square root of 2 triangle. So because of that, this has to be 45 degrees. So let's say that you forgot that and you don't know that. So if we're going to solve this, we're going to use inverse tangent. So we're going to find the inverse of our side ratio to find the angle. And that inverse tangent of 1 is going to give us our angle. And so let me show you how we do this. So on your calculator, you have tan, and right above it we have inverse tan. So second tangent gives me inverse. I'm going to put a 1 in there because I want to know what happens when my side ratio is 1, and it tells me that my angle is 45 degrees. So inverse tan just works backwards, and it gives you the angle when you have the side ratio. Hopefully that was an easy one. Okay, so find the number of feet of steel cable needed for the zip line. So remember, this is my zip line right here. And so if this is my zip line, this is just a Pythagorean theorem problem. So I have 50 squared plus 50 squared equals my zip line cable. And so when I plug this in, and sorry, this is squared. So x squared plus y squared equals z squared. So what I get when I do this, I'm going to just plug this all into my calculator. So 50 squared plus 50 squared is going to equal just z. So when I plug this in, I'm going to do square root of 50 squared plus 50 squared. And I'm just putting it in as one long sentence. All right? And what I get is that I need 70.7 feet of cable. Cable. All right, let's try another one. So we're in a machine shop, and we want to create this tapered shaft that has a diameter of 5 centimeters at the small end. So if it's tapered, it means it's going to get bigger at the bottom, right? So think like a cone. It's getting bigger as we go this direction. All right, so 5 centimeters at the small end. So here's the small end. This is going to be my big end. And the whole thing is 15 centimeters long. So this whole thing is 15 centimeters long. The taper is 3 degrees. So that's saying that this angle right here, as it gets bigger, this angle right here is going to be 3 degrees. Find the diameter D of the large end of the shaft. So we want to know this diameter. Okay, so what we're looking for is we're looking for this distance x right here, because what's going to happen is we know, let me use a different color here. I know that from here to here, that my taper is going to be the same. So I know already that this distance that's right here, if I draw my line across and I draw this line, if I draw this line across, because this is a 3 degree taper, this distance is going to be 5. So what I want to know is, what is this distance x? And when I have that, guess what? I'm also going to have the same distance x here. So my overall formula here is going to be, D is going to be the radius of the small side. So the radius of the small side, which is this 5 right here, plus 2x. I have x up here, and I have x down here. Okay, so I have to find x. Well, if I know that this is 15, and I know that this angle here is 3, what I want is this value of x. So what do I have? I have this opposite side, and I have my adjacent side. So I'm going to have tangent of 3 is going to be x over 15. So when I solve this, I have 15 tan 3 equals x. So if we plug this in our calculator, we have 15 tangent of 3, and that's 0.786. That's my x value. So when I plug the whole thing in, my diameter is going to be 5 plus 2 times 0.786. So my diameter of the fat end of my little rod here is going to be 6.6 centimeters. Okay, this one's a little tricky because, you know, conceptually you have to do this. And what I would tell you on every single application problem, you have to draw a picture. All right, so here's where we go. We have a building, it says the maroon building. Is that how you spell maroon? Anyway, the maroon building and the black building are 45 meters apart. And from a window in the maroon building, so here's my window, the angle of elevation to the top of the black building. So the angle of elevation to the top. So this 39 degrees is actually this. It's the angle of elevation. So here's my horizontal. So as I look up, this is going to be 39 degrees. So I'm going to get rid of that because it's a little bit confusing. Okay, from the same window, the angle of depression to the base of the black building is 48 degrees. So this angle right here is going to be 48 degrees. So we haven't talked about this concept here of angle of depression, but angle of depression means we are going to look down. And this is always, I didn't write this earlier, but it's always from the horizontal. So here's my horizontal. So if I'm looking down, that makes this angle here 48 degrees. All right. And let's see, what else do we know? I guess that's all we know. So here's what we do have. We do know that this distance between these two buildings is 45 meters. That makes my horizontal, that makes this 45 meters. All right. So let's go down here. Find the height of the window in the maroon building. The height of the window in the maroon building. So what I want to know is, what is this distance here? And I'm just going to call this X. That's the window that I have. Well, if I know that this angle is 48 degrees, then I can calculate this angle right here. But here, let me do this real quick, just so that you've got that data point. So I know that this is a 90-degree angle. And if I have 90 and I minus 48 degrees, I have a 42-degree angle. So this angle here that I scribbled out, this is 42 degrees. And what I know is I've got this side here, which is my opposite side. And what I want to know is this value of X. So if I have this angle that's 48 degrees, then this angle is 42. So I can say tangent of 42 is going to be my opposite side, which is 45, over what I want, which is my window, which is X. So if I rewrite this, I'm going to have 45 divided by tan of 42. So the X has to come out of the denominator. So the X comes up here, and then the tan 42 comes down here. So if I put this in my calculator, I have 45 divided by tan of 42. And I get that this distance, this blue X distance to the height here is going to be 49.977. So I'm going to say 50 meters. All right. The next part of this question says, what is the height of the black building? Well, here's what I know. I already know that this height right here is going to be 50 meters. We just calculated that. So if this is the window, if I draw this from the horizontal, then I know this part is 50. So what I'm looking for now is I'm looking for this distance y, right? I'm looking from here to here. This is going to give me that distance y, and then I'm just going to be able to add those. Well, this one's easy because I already have my angle to my horizontal. And so what I have here is tangent of 39 is going to be y over 45. So it's y over x. So if I rewrite this, I'm going to have 45 times tan of 39. So if I plug this in, I have 45 tan 39, and that gives me 36.4. So that's this y distance, this pink distance, but I have to add the 50, that is this blue distance up to the window. So this is going to give me a total distance of 86.4 meters. Okay, ladder problems. So ladder problems are really, really common in calculus and in actually even on the SAT because we can make a right angle very easily. So it says a 25-foot ladder positioned against a wall forms a 70-degree angle with the ground. So here's what I have. So I have some wall that's right here, and I have this right here. I have a 25-foot ladder. And it says that it forms an angle of 70 degrees with the ground. That's going to be this. So this angle with the ground, this is also an angle of elevation. How high up the wall does the ladder reach? Well, I drew this so that it goes all the way up the wall, but we don't know that. So this is the distance that we want. We want W here. So what I have is sine, which is opposite over hypotenuse. This created a right angle as I put my ladder here. So I have sine of 70 degrees, and that's going to give me my wall over 25. So when I plug this in, 25 sine of 70, it tells me that it's 23.5 feet up the wall. Okay, now the second question says, how far is the base of the ladder from the wall? Well, here's my wall. This is what I want to know. So this time, I don't know this, and I'm just going to say B for base. Well, I'm going to use the same values, but now I have my adjacent side. So this is going to be cosine of 70 degrees, and that's going to be the base over 25. So if I plug this in, 25 cosine 70, I get 8.55, so I'm going to say 8.6 feet. Okay, last question. It says, if some obnoxious student tips the ladder back without moving its foot. So you're taking the ladder and you're tilting it this way, right? You're tilting the ladder. It will reach a window on the other side of the street 11 feet above the ground. So here was my original ladder, right? And I'm going to take it and I'm going to tip it. And now my ladder is over here, right? So here's my ladder. And now I know that it's going to be 11 feet off the ground. So here's what I have. This is 11 feet above the ground. How wide is the street? Well, here's what I know. I already know the base of this side of my ladder, right? So this was when it was at the first wall over here, and I know that this base is 8.6 feet. Okay, so now what I'm going to do is I'm going to take this ladder and I'm going to tip it over here, and this is what I need because this is my street right here. So I need to know what is this overall distance that I have. Well, I cannot assume that this angle and this angle are the same, right? And so I can't say, all right, if this was 70 degrees, this is 70 degrees. I don't know that, right? It could be, I drew that so that it looks this way, but it might be that my ladder is here, right? This wouldn't be the same. So even though I drew it so it looks like they're pretty similar angles, that's not necessarily true. The only other thing that I know is that my ladder length didn't change. We're going to assume that this is some ladder that's going to stay the same, right? It's not necessarily going to be some collapsible ladder. So what I have now is I have this side and I have this side, so I can use the Pythagorean theorem to find this side. I have x squared plus 11 squared equals 25 squared. So if I look at this, I would have square root of 25 squared minus 11 squared, and that gives me a distance of 23.4 feet. So this distance right here is 23.4 feet. So if I want the distance of this street, and I'm assuming that this is the street, it's going to go wall to wall, I'm just going to add these two. So I have 23 point, oh gosh, why did I write 23? It's 22. Sorry, 22.4. And I'm going to just add 8.6 to this, and I get a total distance of 31. So this is 31 feet wide. Okay, I'm sure there are a lot of other questions on here that we're going to practice in class just to give you some more ideas of how we can use this application.